This is Physics 1060, Descriptive Astronomy, Lecture 11. Today we'll be going through Chapter 10. The main themes of this section will be how we can analyze the light from stars to understand them, how other stars are different from our Sun, how stars change in time, the origin of all the elements, and we'll also talk about strange things like neutron stars or black holes. So, how do we measure the properties of stars? With very few exceptions, we don't see details of stars. They're not star-shaped. We assume they're round like the Sun. We have to analyze the light from the stars then in ways that the naked eye can't. So those tiny glints of light in the night sky are in reality very huge, dazzling balls of gas, many of which are vastly larger and brighter than the Sun. They look dim because of how far away they are. Now, we can't probe stars directly. We can't go and make a measurement or dip a cup in to take a cup of star matter and figure out what it is. So we have to come up with indirect methods to ascertain their properties. Measuring distances to stars and galaxies is not easy. And distance is a very important number for determining lots of the intrinsic properties of astronomical objects. So one way of determining distance is triangulation, where we would measure a triangle, and so we have a baseline, and then we have maybe a 90-degree angle, another angle, and if we know a baseline and two angles, we can figure out the distance away something is. We use trigonometry or a scale drawing to determine how far it is. And in astronomy, we can use trigonometric parallax. So, for example, the stars that are really, really far away will not move depending on where the Earth is around the Sun. They're too far away. But a star a little bit closer will actually look different. If you take your thumb and hold it out at arm's length and close one eye and put it over some object in the distance or on your wall, now switch eyes. Now, your thumb appeared to move against the background stars. It didn't really move, but because of parallax, because I'm looking at it from slightly different places, it changes its position on the background. We do the same thing here. We'll take a picture of the sky and we'll look at a star here in January, and that star will appear to be here in the background. Then 6 months later, when the Earth is on the other side of the Sun, we can look and it appears to be somewhere else. And I can measure the angular distance of the two places it looks like in the sky. If I know that angular distance, this angle here will be half of it. My baseline is 1 astronomical unit. That's a big baseline. This is a 90-degree angle, and now I can determine how far it is from our solar system to that star. Again, looking at it from above, you can see this right triangle a little bit better. This is called parallax. The baseline is Earth's orbital radius, and angles are measured with respect to very distant stars. The shift of nearby small stars is really small. The angles are actually measured in arc seconds. And the parallax angle, P, is half the angular shift of the nearby star, and its distance in parsecs is given. A parsec is a unit of distance that we use for stars close by to us. It's 3.26 light years. It's kind of the average distance between stars in our neighborhood. Now, parallax is really only useful to stars that are about 250 parsecs or closer. So we can even look at an example. Sirius is also known as the dog star, and it's one that's fairly close. And we can see the parallax angle for it is 0.377 arc seconds. And remember, an arc second is a 60th of a minute, arc minute, which is a 60th of a degree, which is 1 over 360 degrees around a circle. So from the formula, the distance, you don't need to know this formula. It's 1 over the angle, and it's 2.65 parsecs, or Sirius is about 8.6 light years away. Another method for determining distance is called the standard candle method. Now, if an object's intrinsic brightness is known, its distance can be determined from its observed brightness. So, in other words, if we know how bright a star is from some other method, and we know how bright it appears, we can tell how far it is. You could do this in a lab too. If I knew I had a, say, 100-watt light bulb, and I put it at some distance away, I took another 100-watt light bulb and I put it close by in a distance I could measure. I took a photograph of it. The diameter of the circles of on the picture of the light from that, the ratio of that would be the same as the ratio of their distances. This is actually the principal manner in which astronomers determine distances in the universe. So light is the astronomer's tool. We want to know motions, sizes, colors, and structures of stars. This information helps to understand the natures of stars as well as their life cycle. The light from the stars received at Earth is all we have available for this analysis. Now, the color of a star indicates its relative temperature. Blue stars are hotter than red stars. More precisely, a star's surface temperature in Kelvin is given using Wien's law. Remember, we look, and the maximum brightness of, if we look at all the different wavelengths, the ones that's the peak tells us something about the temperature in Wien's law. So by just looking at what color is the maximum brightness, we can determine the temperature of a star. Now, luminosity is a property of a star that tells the amount of energy it emits each second. And luminosity is usually abbreviated with a capital L. A typical unit of measurement for luminosity is a watt. So, a 100-watt light bulb tells you its luminosity. The sun's luminosity is 4 times 10 to the 26 watts, or 4 million billion 100-watt light bulbs. Luminosity is a measure of a star's energy production, or in other words, how fast it's burning hydrogen fuel. So knowing a star's luminosity will then allow us to determine the star's distance and radius. The inverse square law relates an object's luminosity to its distance and its apparent brightness, how bright it appears to us. The law can be thought of as the result of a fixed number of photons that once the photons come off the object that's giving light, they continue to go out, so they spread out evenly in all directions as they leave the source. So then the photons have a larger and larger concentric spherical area that they go through. So for a given shell, the number of photons per unit area decreases. If I think of this light bulb here, and I have, say, 36 photons coming through this 1 meter square area at a distance 1 meter away, those same 36 are now spread over, when I'm 2 meters away, over 4 square meters. So now there's only 9 photons per square meter. And I have the same number of photons going through all of these, but the area that they are spread out over is getting larger. So the number of photons per unit area decreases. The inverse square law then it becomes the brightness of an object is its luminosity divided by 4 pi d squared, where d is the distance away from the object. This relationship is called the inverse square law because the distance appears in the denominator as a square. The inverse square law is one of the most important mathematical tools available to astronomers. Given, say, distance from parallax measurements, a star's luminosity can be found, because a star's brightness can be easily measured by an electronic device called a photometer. We can connect it to a telescope, measure its brightness. Once we know its distance, we know its luminosity. However, the real power to this becomes if I know the luminosity in advance due to something, and I can measure its brightness, I can then calculate its distance using the inverse square law. Now, another thing we might want to know is radius. So let's use some common sense here. Two objects of the same temperature but different sizes. The larger one radiates more energy than the smaller one. Just imagine if I had, say, a BB and a large cannonball and I put them in a fire and they're glowing orange hot and I take them out. The larger one is going to radiate more light. It's going to be brighter. They're the same temperature, but the larger object gives off more light. In stellar terms, a star of larger radius will have a higher luminosity than a smaller star at the same temperature. So how do I know the luminosity in advance? First, we need to know how much energy is emitted per unit area of a surface held at a certain temperature. There's another law in physics. I'm just letting you know how this works. The Stefan-Boltzmann law. You don't need to know how to use it, just that it exists. It says the brightness of an object is equal to some constant, that's the Greek letter sigma, times its temperature to the fourth power. Now the Stefan-Boltzmann law applies to stars, but not hot, low-density gases. We can combine the Stefan-Boltzmann and the inverse square law then to get that the luminosity is 4 pi r squared sigma t to the fourth, where r is the radius of the star. Now let's look at this. If I know now the temperature from Wien's law, and I know the luminosity somehow, I can now find how big the star is, or its radius. So putting it together, I have the total energy radiated per second by the star as its luminosity. That's the energy emitted by 1 square meter times the number of square meters on its surface, which would just be sigma t to the fourth times the star's surface area. And if it's a spherical star, the surface area is 4 pi r squared, so that's how I get this all together. You do not need to know how to derive or put these equations together. I just want you to see how a scientist uses fundamental laws that they can determine, and they start to combine them to be able to use them to measure things that you wouldn't think that you could measure. By looking at energy output and temperature, I can figure out a radius. Now, the methods using the Stefan-Boltzmann law and interferometer observations show that stars differ enormously in radius. Some stars are hundreds of times larger than the Sun, and we call those giants. And others are smaller than the Sun, and we call those dwarfs. So for example, the same star we were talking about before, Sirius, if we solve for the star's radius, it can be simplified if we apply this equation to both the star and the Sun. It's another thing that scientists like to do. Instead of having to solve each thing, we just take the equation for one, divide it by another, and we can get a relationship between things just by looking at ratios. And if you do, you can get this equation. It says the radius of a star over the radius of the Sun. That symbol, a circle with a dot in it, is the mathematical symbol for our Sun. So this means the radius of the Sun, the luminosity of the Sun, the temperature of the Sun. We use our Sun as a astronomical unit of different things. So, for Sirius, we know that its luminosity is 25 times the Sun's. It's 25 times more energy output than our Sun. Its temperature is 10,000 K and the Sun was 6,000 K. And therefore you put that together and we find that the radius of Sirius is 1.8 times the radius of the Sun. Now another way of looking at stars is something called magnitude. And in 150 BC, Hipparchus was a Greek astronomer, and he measured the apparent brightness of stars using units called magnitudes. The brightest stars in the sky had a magnitude 1, and the dimmest had a magnitude 6. Now this system is still used today, and units of measurement are called apparent magnitudes to emphasize how bright a star looks or appears to an observer. This would be the brightness. A star's apparent magnitude depends on the star's luminosity and distance. A star may appear dim because it's either very far away or it doesn't emit much energy. Now apparent magnitude can be confusing because the scale runs backwards. It's a logarithmic scale. High magnitude means low brightness. And modern calibrations of the scale actually create negative magnitudes for things like the moon and the sun. Magnitude differences equate to brightness ratios. So a difference in 5 magnitudes is a brightness ratio of 100. Now all these numbers down here are just based on logarithms. It's a logarithmic scale. So astronomers use absolute magnitude to measure a star's luminosity. The absolute magnitude of a star is the apparent magnitude that same star would have at 10 parsecs. A comparison of absolute magnitudes is now a comparison of luminosities, and there's no distance dependence. Now the next thing we can see with the light from stars is its spectrum, and it depicts the energy it emits at each wavelength. The spectrum can also reveal a star's composition, its temperature, its luminosity, its velocity or speed in space, how fast it's rotating, and other properties. And on certain occasions it can even reveal the mass of a star and its radius. So being able to figure out the spectra of a star is a very important measurement. So as light moves through the gas of a star's surface layer, the atoms there absorb radiation at some wavelengths, and that creates a dark absorption line in the sun's and the star's spectra. Every atom, we've learned, creates its own unique set of absorption lines. So determining a star's surface composition is then just a matter of matching a star's absorption lines to those known for atoms. So to find the quantity of a given atom in a star, we use the darkness of the absorption line. The darker or wider the absorption line, the more material there is. This technique of determining composition and abundance can be tricky. There is possible overlap of absorption lines from several varieties of atoms being present, and temperature can also affect how strong or how dark an absorption line is. So how does temperature affect it? A photon is absorbed when its energy matches the difference between two electron energy levels and an electron occupies the lower energy level. At high temperature, there's lots of collisions and energy exchange, and sometimes force the electrons on average to occupy higher energy levels. Lower temperatures are lower electron levels. So at higher temperatures, sometimes light's not absorbed at a certain place because there's no electrons in that place. Consequently, absorption lines will be present or absent depending on the presence or absence of an electron at the right energy level, and this is very much dependent on temperature. So, if we do that and we adjust for temperature, a star's composition can be found. And interestingly, virtually all stars we see in the sky have very similar composition to the Sun, about 71% hydrogen, 27% helium, and about 2% the mix of the remaining elements. This is an important piece of information when we're trying to look at the structure of the universe as a whole. Now historically, stars were classified into 4 groups according to their color: white, yellow, red, and deep red. And those were subsequently divided into classes using the letters A through N. Now Annie Jump Cannon discovered the classes were more orderly in appearance if we rearranged those by temperature, not by color. Her reordered sequence became O, B, A, F, G, K, M. O and B being the hottest stars and M the coolest. And today these are known as spectral classes. Cecilia Payne then demonstrated there was a physical connection between temperature and the resulting absorption lines. So if we look at the spectra for different stars, this is an O-type star, B, A, down to an M-type star, you see that the spectra are different. The cooler stars have more transition levels in the visible, so you get more dark lines. Whereas an A line, an A spectra, there's some lines that really aren't visible that become very strong in an A-type star and start to weaken again. So which absorption lines I get depend on the temperature of the star. Now, O, B, A, F, G, and everything are also going to be subdivided into different classes. So, and an O star is going to be 35,000 degrees Kelvin at its temperature. We said the Sun is right around here. It's a G-type star. And notice here, this is kind of a finer graded absorption spectra, and you can see how some spectra here fade out depending on temperature. Some grow and then fade out at higher temperatures. And so then by looking at the spectra, I have a better way of measuring temperature than Wayne's law. O stars are very hot, and the weak hydrogen absorption line indicates that hydrogen is very ionized in the hot stars. A stars have just the right temperature to put electrons into hydrogen's second energy level, which results in strong absorption lines in the visible light. F, G, and K stars are low enough in temperature to show absorption lines of metals like calcium and iron, elements that are ionized in hotter stars. And K and M stars are cool enough to form molecules, and the absorption bands become evident. A molecule might absorb over a band or a wide area of wavelengths as opposed to just a very specific one. The temperature, the surface temperature, ranges from more than 25,000 for K and O stars to less than 3,500 degrees Kelvin for M stars. Again, spectral classes can be subdivided by numbers. The Sun is a G2 star. Now, I said we can also measure a star's motion from spectra. We can determine that from the Doppler shift of its spectral lines. The moving of certain spectral lines, we know where they are, either one to the red side or the blue side. The amount of shift depends on the star's radial velocity. That's the star's speed along our line of sight, how far it's moving towards us or away from us. Given that we measure a shift delta lambda, delta just means change in mathematics, and lambda is our wavelength. So the change in wavelength over what we know the wavelength should be times the speed of light gives us the velocity. We can measure the star's velocity coming towards us or away from us with very good accuracy. So lambda is the wavelength of the absorption line of an object at rest, and its value is determined from laboratory measurements on non-moving sources. An increase in wavelength means the star is moving away. I get a red shift. A decrease or a blue shift means it's moving towards us. Now, any speed across our line of sight can't be determined, only speed coming towards or away from us. Doppler measurements and analysis show that all stars are moving and that those near the Sun share approximately the same direction and speed of revolution, about 200 kilometers per second, around the center of our galaxy. Superimposed on this orbital motion are small random motions of about 20 kilometers per second. In addition to their motion through space, stars spin on their axes, and the spin can be measured using Doppler shift techniques. Young stars are found to rotate faster than older stars. Now, another thing as we see as we look out are binary stars, two stars that revolve around their mutual center of gravity. Binary star systems offer one of the few ways to measure stellar masses, and stellar mass plays a leading role in a star's evolution. At least 40% of all stars known have orbiting companions, some of them more than one. Most binary stars are only a few astronomical units apart, and a few are even close enough to lightly touch. We have different types of binaries we see. The first is a visual binary. They're systems where we can see the orbital motion of the stars around each other by comparing images made several years apart. So I'll usually have a larger star and a smaller star, and they will be rotating around this common center of mass. The next is called a spectroscopic binary. They're too far away or too close together that we can't actually see two stars. But as we look at the spectra, we see that there are two lines and they move apart from each other and towards each other, apart from each other and towards from each other. And so Doppler analysis of the spectra then gives us the star's speed by observing a full cycle of the motion of the orbital period, and then we can determine their distance from each other. Now Newton modified Kepler's third law. The mass of the two stars times the period of revolution is their distance away from each other. And if I know their distance and I know their period, I can determine their masses. P and A are determined from observations, may take several years, and the above equation gives their combined mass. And further observations of the orbit allows the determination of each star's individual mass. What we see is most stars fall in this narrow range of about 10% of our Sun to about 30 times the mass of our Sun. The next kind of binary that we can see is something called an eclipsing binary. These again are stars that are too far away that we can't see two different stars, but I can look at the light coming from it. And when the two stars are side by side, even though we can't resolve them, we're getting light from both of them. And then as the smaller star goes in front of the larger star, it's blocking some of the light, and so it goes dim. Then it comes out from behind and it goes bright again. Now, when that smaller star goes behind it, I also lose some light, and it's not as much. So now, by looking at this distance here in time, I can measure the period of these stars. By actually looking at how much light is blocked off and the ratio, I can actually figure out the ratio of their radii by looking at how much light is blocked off. So the duration and manner in which the combined light curve changes together with its orbital speed allows astronomers to determine the radii of the two eclipsing stars. So let's kind of summarize the stellar properties we've looked at so far. We've looked at distance. We can use parallax for nearby stars and the standard candle method for measuring the distance to further stars. Temperature, we can either use Wien's law or spectral class to determine its temperature. Luminosity, we can measure the star's apparent brightness and distance and then calculate it using the inverse square law. Or we can talk about luminosity class just by the spectrum. We haven't talked about that, but it's another way of determining luminosity. And we can also measure its composition, the spectral lines observed in a star. We can measure its radius using the Stefan-Boltzmann law to measure luminosity and temperature, solve for radius. We can use an interferometer, which gives angular size of the star from distance and angular size for nearby stars. Or we can use an eclipsing binary light curve to determine radius. Mass, we use Kepler's third law applied to binary stars. And radial velocity, looking at the Doppler shift of the spectrum lines. So all this information is determined just by looking at the light of the stars. Now, we've done this. We've measured all these properties of all these different stars. Now we're trying to get a big picture. How do we put it all together? The next step, of course, now is to understand why stars have properties in the combinations observed. And this step in our understanding comes from the HR diagram, developed by two different scientists, Injar Hertzsprung and Henry Norris Russell, in 1912. The HR diagram is a plot of stellar temperature versus luminosity. Now, when we do this, most of the stars on the HR diagram lie along a smooth diagonal running from the hot luminous stars in the upper left of the diagram to the cool dim ones in the lower right part of the diagram. By tradition, bright stars are placed at the top of the HR diagram and dim ones at the bottom, while high temperature stars are on the left and cool ones on the right. Now, when you normally see a graph, it usually starts out with low numbers to high numbers. So that's backwards on the temperature here. And that's just by tradition, and we're pretty well stuck with it at this point. So, in the HR diagram, stars over here are hotter than the ones over here. and the ones down here are dim, and the ones up here are bright. The diagonal running group of stars on the HR diagram is called the main sequence. Generally, in any group of stars you look at, 90% of the group of stars will be on the main sequence. However, a few stars will be cool but very luminous, the upper right of the HR diagram, while others will be dim and very hot, the lower left of the HR diagram. The Stefan-Boltzmann law is the key to understanding the HR diagram. For stars of a given temperature, the larger the radius, the larger the luminosity. Therefore, for a given temperature, as one moves up the HR diagram, a star's radius must become bigger. On the other hand, for a given luminosity, the larger the radius, the smaller the temperature. Therefore, for a given luminosity, as one moves right on the HR diagram, the star's radius must increase. The net effect is that the smallest stars are in the lower left corner and the largest stars are in the upper right. We can actually then plot the radius of stars on our HR diagram. The ones down here are about 1/100th of the size of our Sun. And as we get further and further here, we get ones that are 1,000 or more times the radius of our Sun. Those stars in the upper left are called red giants. They're red because they're low temperature, and that therefore they're going to be more red than white. Stars in the lower right, then, are white dwarfs. And so we have three stellar types: main sequence, red giants, and white dwarfs. Giants, dwarfs, and main sequence stars also differ in average density, not just diameter. Typical density of main sequence stars is about 1 gram per cubic centimeter, while for a giant, it's 1/1,000,000th less. Now, when putting all these all together on the HI diagram, another relation was discovered: the mass-luminosity relation. Main sequence stars obey this, and it's approximately given by the luminosity is equal to the mass cubed, when luminosity and mass are measured in solar units. So consequently, stars at the top of the main sequence are more massive than the stars lower down. Now, another method was discovered to measure the luminosity of the star, other than its apparent magnitude and inverse square law. It was noticed that some stars had very narrow absorption lines compared to other stars of the same temperature. It was also noticed that luminous stars had narrower lines than less luminous stars. So the width of the absorption line depends on density: wide for high density, narrow for low density. So then if I look at the high and low density stars, even the same spectra, you see they're wider for high density than they are for low density. So luminous stars, and again in the upper right of the HR diagram, tend to be less dense, hence they had narrow absorption lines. So now the HR diagram can be broken into luminosity classes. 1, the bright supergiants, 1A, and 1B, the supergiants, 2, the bright giants, 3, giants, 4, subgiants, and 5, the main sequence stars. So now the Sun is a G2-5 star. Right, to summarize these, most stars lie on the main sequence. Of these, the hottest stars are blue and more luminous, while the coolest are red and dim. A star's position on the sequence determines its mass, being more mass near the top of the sequence. And we have 3 classes of stars. We have the main sequence, we have the giants, and we have the dwarfs. Not all stars have a constant luminosity. Some change in brightness, and we call those variable stars. There are several varieties of stars that vary and are important distance indicators in astronomy. Especially important are the pulsing variable stars, stars with rhythmic swelling and shrinking radii. 2 different types are the Mira and the Cepheid variable, and they're classified by the shape and period of their light curves. The Mira stars, the period is sometimes over several hundred days. So in this case, the period is 200 days for this star. The Cepheid variables are a short period variable star, and their period is 3 to 4 days. Now if we look at variable stars, they lie on something called the instability strip, the strip on the HR diagram. Notice stars like Polaris or North Star are variable stars. This concludes everything we're going to talk about in Chapter 10.